I went to the Rhode Island School of Design for the Industrial Design program, and during it I became interested in robots, so I revived an old plotter, a pen plotter that I found. I got really interested in the work of Bruce Shapiro, who's been doing a long series of interesting CNC art pieces, such as a sand sculpture called Sisyphus. Does a bunch of projects drawing with bubbles and interesting applications of computer-controlled machines. I wanted to play with that more. I built an egg plotter based off of his designs and took a class in basic electronics at RISD, and decided I wanted to go further. And so during school, I applied for a bunch of internships with robotics companies, starting with more traditional robotics companies like Boston Dynamics, the company that does Big Dog. And after that didn't pan out, most of the companies were looking for solid engineers, and I had a fabrication and industrial design background. I had a portfolio of mechanisms, and I was going to an art school. I also had a portfolio of drawings, paintings, illustrations, technical art. So I went further afield and ended up landing in the special effects industry making movie monsters. And so I worked on Snakes on a Plane, I worked on Team America World Police, I worked on Alien vs. Predator, so I ended up getting my experience through robotics in this interesting field that sort of fit my off-center experience in art and engineering up until that point. And so I've been trying to take it further ever since. So in the general field of robotics, my first steps were, as a kid, making robots from broken toys, and playing with Lego Mindstorms. And as I got sort of more sophisticated with things, designed, robots. I designed a robot to follow me around. In Halloween, I was Luke Skywalker, and I designed a little remote-controlled R2-D2. But sort of in the field of soft robotics, in the field that I'm pursuing now, my first forays were really in the special effects world. Learned a lot of mold making, casting, materials design, working with elastomers, and especially in doing animatronics, you usually regulate the wall thickness that you're using in the silicone or whatever material you're using, say, for a creature's face. You control the thickness, the way the material pools, the durometer, the way it's folded to try and get the dynamics correct so that it expresses, so that it doesn't look like a prop and comes to life. There's a visceral feeling when you get those measurements correct. So I pursued that for a number of years, and in seeing soft robotics prototypes coming out from universities, over time I felt that I too could make innovations in the field, but needed to figure out a manufacturing method that sort of agreed with my method for development. I like iterating, I like rapid prototyping, but I want things to be very finished and complete. I like for them to speak for themselves as much as they can, and I like for them to have a good quality of finish. And so I figured out methods for 3D printing molds and casting them with, say, soluble cores or removable cores to form the pneumatic elements while also being seamless with seeming like a finished product, seeming like a robot that stands on its own, that I can, tuck in all of the loose hairs to have it be a finished, complete object. And so my first experiment with that was at Jim Brett's lab. Jim runs a 3D printing company or 3D printer development company called Viridis, and so we started collaborating on he working on the materials that a soft robot could be made of and the methods for printing it on a powder printing machine, and I worked on the design and the manufacturing method, and we came up with some really interesting prototypes. And I made a couple of tentacles, I made a couple of mechanical actuators, did experiments with embedding materials in silicone, and that's where I got my start. So the idea behind the company is that soft robotics has a number of useful applications. And if you think of soft robotics in a design for manufacturing perspective, you start realizing that they could be applied to practical problems, but aren't in many cases because the field is very academic, the field is very research-based, and there's an opening for applications. There's an opening for companies that want to develop practical solutions inside of soft robotics. So it sort of became my choice to decide to pursue an individual product like a medical device and attempt to build a company out of soft robotics that way, or to become an R&D lab and continue trying to create new methods for making a soft robot fundamentally, or figuring out how to prototype something in a context that reflects how the end manufactured product is going to perform. So ways of building and designing in a format that tells you about the end product. And I was really excited by the possibilities, excited to sort of proselytize soft robots as a general field, as a method for solving problems, as being something useful for humanity. And so I've been pushing it ever since. You know, it started with a couple of projects and making things and editing video and, you know, creating backdrops in my house and figuring out how to sort of sell the idea of soft robots. And as I've gotten better at the designs, the things that I release have gotten more popular. I also publish in the open source. So I'll publish a design and I'll release all the design files and I'll release my lab notes and I'll try to show people the various things that went into it. And it helps both validate the research that I'm doing, making it scientifically testable, as opposed to describing the dynamics of the robot. A researcher can actually print and build their own version of my robot to prove that I'm not fibbing about the dynamics. But it also helps spread the word. It also helps show the kind of engineering that I do. And so that helps to bring in clients and sort of prove the reliability of the methods that I'm going on about. So I'm the core of Super-Releaser, and then Jim Brett has his own lab, and we still collaborate on projects. I also have a couple of contractors that I end up using, like an artist, Colin Foran, has been doing a lot of prototyping of ideas for medical devices. So I have pretty fine control over the aesthetics of these robots. And so I'm able to decide how the mechanisms should appear. And so I've been working with him, he's a game concept artist, to develop how an orthotic, an active orthotic, should look. I work with a soft goods engineer who does both Broadway costumes and spacesuits, Carrie Love. And she's very helpful for figuring out how things fit to the body well, because she's had to fit a lot of costumes to a lot of bodies, where adjustment is necessary, where adjustable straps and Velcro is useful in design, and where elasticity is essential, and helping draft patterns to complete those goals. So it's a small team, very broad backgrounds, sort of art and science running in parallel. But it ends up being an exciting collaboration between all of us. So I met Jim Brett through a mutual friend in Somerville, an artist friend who also does a lot of programming. And it sort of grew from there. He had machines that he needed to prototype lots of different printing materials on, and so it was constantly running prints, and so it was sort of an idle change to his sort of modus operandi to just put my parts on his machines, and it was sort of a fun side project. And as we got more serious about the soft robots, you know, we both ended up spending more time on it. Carrie Love, I met her through a mutual friend in the publishing industry, And we started collaborating after I learned about her work at Final Frontier Design. So she does a lot of work stitching and designing and stitching spacesuits at Final Frontier, which is a company in the Brooklyn Navy Yard that does a lot of contract spacesuit development for NASA. Um, so it built from there, and we sort of developed skills to grow in tandem, but we also helped define a nebulous field. Soft robotics can be many, many things, to point towards some goals and some ideas that we have about the manufacturability and the purpose for soft robotics. So I do soft robotics partially because it's a good blend of the skills that I have. It's entertaining to bring the various experiences that I've had from the special effects industry, from industrial design, from product design, fabrication. I was a machinist for years. I know, workflow and process control. Um, it's it's exciting to feel that I'm innovating in a young field, building things that other people can't build or don't have the experience yet to build, and that I can bring something useful into people's lives if I design and build correctly. That if I pull off all the things that are sort of on my checklist of design goals, then on the other end, people will actually get a tangible benefit out of what I'm doing. So the projects that I'm working on right now, I just got a contract from NASA through an SBIR grant to do development of spacesuit glove components. And so I'm spending a lot of my time figuring out how to do molds with that control very thin wall thicknesses that are very predictable and reliable for making wrist dams and things to control the amount of air that's moving through components in the spacesuit. Specifically, there's an idea in spacesuit design to do this thing called mechanical counterpressure, where the usual spacesuit has a layer of air between the person and the suit, and then after that you have space. So the way that the suit puts even pressure across your body is really just the air tries to even pressure out all over the system. But it creates a number of problems. In addition to there being a giant gas spring formed by the entire suit, it also means that there's a large amount of space between you and the outer walls of the suit, making dexterity fairly low. It means that the suit is very difficult to maneuver in a lot of contexts. It's very tiring, especially for doing dexterous tasks over a long period of time. The suit doesn't do a perfect shape change all over. So things like finger cups in the suit don't precisely match your finger geometry. Now, whether it's hotly debated why your fingers sort of fall apart in space, but one of the culprits seems to be that your body at rest in the gravity well is a different shape than it is in space, and this includes your fingers. And so you go into space and you have these finger cups that are in the gloves, and your fingers change shape, and you work in those gloves for 8 hours, and your fingernails delaminate. So there are a lot of problems that NASA feels could be solved by changing the dynamics of the glove itself, and that is using cloth to perform the stretch limiting, the tensioning of the body to prevent shape change due to the vacuum. So one of the potential advantages for that is having no air in the system, but even using the body's own cooling system, sweating, directly out into space to do heat control. That means that they need to cut off air from the rest of the suit because they're only doing it component by component. And so the majority of what I'm working on this grant is methods for cutting off pressure without cutting off circulation, without creating long-term bruising, without creating any stress on the body, really. And so that means a lot of components that are very controlled in their wall thickness, so have a very predictable, even thickness, have cores, when they're molded, that have cores that register in an exact spot that that avoid lamination and adhesives, that star embedding components, like embedding seamless knits in the interior of the wrist dam that I'm designing at the moment. Or actually, I've got physical prototypes. The general purpose being to interface smoothly with the body. And this involves a lot of the kind of prototyping that I've become known for. What was my first real project? So my first real project in soft robotics was probably a thing called the trefoil tentacle, which was an experiment in wax core molding with this flavor of soft robotics. So I do these seamless elastomer casts with complex cores. And so I figured out that I could print a shell, and actually a rotationally symmetrical shell, so I could print 3 copies of the same shell and bolt them together to define the outer geometry of the tentacle. And then I could actually divide the core, so take the interior shape that I wanted to form the actuators inside of the robot, and make a core of it that had flat areas on it so that I could actually, in CAD, paste all of the core elements to a mold and build up walls around it. And so it gave me the opportunity to actually take the first tool that was made on a 3D printer, pour silicone into that, and pull out a mold that actually forms the wax cores. So I have a silicone mold, and it's very easy to cast wax into silicone. And I used a jewelry casting wax to actually cast the cores so they could be melted out afterwards. It became a process that worked very well for creating quick, accurate parts. I developed the method, actually. It's an extension of the work in the Guerrilla Guide to CNC Machining, which has an excellent descriptions of how to create accurate gears from CNC machined molds. So Google and RISD have a long-running relationship. There are a lot of RISD people who have worked for Google, especially in their lab development sort of portfolio. And so that was sort of my connection there. And then NASA actually puts out a number of grants. Being a government agency, they put out a number of grants geared at small businesses. And so my relationship with Final Frontier Design, I've done CAD and helped them with proposals and done sort of like spot checking on robotic prototypes and pitched ideas with them to NASA. And we've sort of been collaborating on grant proposals for a while. And finally, they landed the mechanical counterpressure glove grant. And I had done some fundamental work for the proposal and put in a bid to do subcontracting for a couple of the major components of the mechanical counterpressure system. And when the grant came through, I became a subcontractor. How are they using my expertise in soft robotics? So I like to think that I am one of the few labs doing results-based soft robotics, where I can have a general problem, like we need to distribute pressure in this way, or we need to interface with a human being in this way, or we need a gripper that conforms to these particular forces or measurements. I believe that my methods for fabricating, designing soft robots are sophisticated enough to tackle this huge range of problems, and I have a portfolio of projects that show expertise in a bunch of elements, in a bunch of areas that are fitted. So where they're using my expertise is I can fabricate a good working soft robot in just about any context. So tiny wall thickness, or highly accurate, or perfect finish, or integrated with other 3D printed components, or graded in durometer. The methods that I've found allow me to quickly iterate, throw a design together, prototype early versions, figure out the molding, build more sophisticated designs in fairly rapid fire. So it gives companies looking to solve practical problems opportunities to work with me in an iterative process so that problem solving isn't black box, and it also is very tied to a practical world where I can find solutions for things as mundane as like how do you create an airtight fastener for a custom silicone component, say a silicone bladder. I have the opportunity to cast things like flanges into the bladder and have fasteners hook into those flanges, and so it can make custom printed fasteners or tailor the, say, silicone bladder to existing fasteners that are known to be airtight. Since the silicones that I use, the elastomers that I use, are very well known and well defined in a material context, they're very consistent. I can actually get very consistent, predictable results from the robots that I'm making. So, soft robotics has huge potential. Soft robotics is a hot topic in research. It is being heavily explored. I think that it's seeing a lot of exploration in a traditional robotics context. So a lot of graspers, grippers, things that you would put on the end of an industrial robot. And I suspect that's because most universities that are using soft robots or exploring soft robots have a robotic arm that is in the lab and they're looking at, thinking, what could go on the end of this robot that's new? I think the future for soft robots is to become broad enough as a field that people who know problem domains, like say work in medical exoskeletons and can see the failures of existing designs, that they have the idea of soft robotics in their head to think this problem could use a soft actuator. This problem could use a compliant device. This problem could use, mass manufacture that makes a device that can, say, deliver power. I'm working on medical exoskeletons right now, and so I have an elbow cuff prototype that can sort of deliver torque to the elbow to be a active orthosis for cerebral palsy. It doesn't matter what diameter your arms are. It doesn't matter if it's exactly matched up with the fulcrum of your elbow, because the compliant mechanism distributes the force across your arm, and the torque on your elbow is predictable even if it's not fit to you custom by a prosthetist. And I think the future of soft robotics is really finding the people who know the problem domains and getting the engineering correct to be able to do predictable device development, to find practical solutions for problems in medicine and human interfaces, problems in robotics and exploration. I'm eager to see the field integrated well with other fields of engineering. That the behaviors coming out of soft robots are different than the behaviors that, say, a traditional robot working on ROS would have, because compliant mechanisms act fundamentally differently than, say, a servo. Does it conform to what I'm aiming at with my research? So I do the research that I do because I believe in this future. I'm excited by the potential of soft robotics finding practical applications, and I try to tailor my research to things that have scalability. I try to always be thinking, if I needed to make 1 million of these, what would need to change about this? And so I try to prototype it in context that respects the need for a successful device to be multiplied, to be affordable, to go outside of my lab, and that it can't just exist as a concept, but actually has to be tied to some level of practicality. So that, in many ways, I do what I do because I see this future. It depends upon how you define soft robots. So seatbelts are compliant mechanisms. Your clothing is compliant. Um, there are a million squirt guns and water balloons and helium balloons and dirigibles. There are all sorts of interesting mechanisms like parachutes and kites and sails that use the same principles that drive soft robotics. We're surrounded by the fundaments of soft robots. What is new is the materials have gotten consistent enough. I've seen the growth of castable elastomers, room temperature vulcanizing silicones, and other elastomers that in my history in the effects industry have gotten much better, much more consistent, much more well-defined, that they're easier to mix. They're almost always 50-50 mix ratios instead of weird esoteric blends. Two-component silicones are everywhere. The CAD software to do the design, although simulation is still very difficult, design is getting simpler and more accessible. The programs still require a run-up. It's not to the point at which anyone can just pick up SolidWorks and go. But it's getting simpler, more accessible. There are new YouTube channels out every day for how to understand CAD and machining and casting. And the quality of 3D printing has really leapt in the last 20 years. You know, even in the last 10. There's been a huge leap in the quality of printing and a huge drop in the expense. And so that means that creating complex forms that involve accurate, shaping of surfaces, that require intimate interfaces, that require custom mechanisms, are no longer thousands of dollars of machining. They're no longer, having a professional model maker on staff. They're no longer having a workshop that you've worked with for 20 years and so have a easy interface for how you spec your drawings so that they can get, tiny shades of difference in how a mold is manufactured. You can now access this yourself. And so I think soft robotics is in this awesome place right now where the enabling technologies that fundamentally drive it are there in a way that they've never been before. It's never, ever been easier. So Solve for X, Georgia Deanist of Solve for X approached me about the research that I had been doing on soft robotics because a lot of my goals are outreach based. I want to prove that soft robotics has a valuable place in the engineering toolbox for solving human scale problems. That it's not an esoteric research field. That it's not an idle pursuit. That if you take the designs seriously, they can solve serious problems. And so she approached me sort of based off of this this spiel I have about robots, this general idea for getting them out there. And she wanted to help me find collaborators, help find people to evaluate some of the things that I'm doing on the back burner, some of the medical device development. So we have medical device clients, but I also build my own prototype medical devices, trying to see what appropriate applications soft robots have. And so finding people to help evaluate them, direct my research to appropriate problems, connect me with other people, is sort of the goal of Solve for X. So I've been doing my best to sort of live up to that and build on the relationships that established. So the most valuable thing for me in terms of being associated with Solve for X is there are people completely outside of my field that I've been in touch with. Specifically, there's a hospital that's agreed to do expert evaluation of one of my medical orthoses. And their expertise is something I would have a very hard time accessing without a resource like Solve for X. The value is in finding people who are willing to volunteer time and experience. So that's been very exciting. Hopefully, the device is going to get sent off in the next couple of weeks, and I'll be able to hear back from them on how accurately I was able to judge the problem domain, and hopefully they'll be able to give me some good feedback on what I need to change to make the device relevant. So it depends on the project. So in some projects, it's important to drive forward with the design um, as a sort of art. There's a there's a way of understanding the problem holistically where you're building the mechanisms in tandem with the manufacturing method, in tandem with the fasteners, in tandem with the control system, and juggling all of those things in your head uh, often ends up being a one-man job. It's something about the field of industrial design that often isn't really known is that many designs, say a Super Soaker, are actually a majority the work of a single person. It depends from company to company. They have different philosophies, but many designs are very difficult to translate to a team. And to do a mechanical design uh, thoroughly, oftentimes there's a phase of evaluation and redlining from other designers, but you're taking care of the whole architecture of the project yourself. In other contexts, though, when I'm not the domain expert, when it's not just about manufacturing a robot in an efficient method, where human interfaces, say, that involve fabric and cloth, um, I'm not the expert on it, although I'm getting quite an education. It's incredibly valuable to bring in people like Carrie to advise and to be a resource. McMaster Carr is a wonderful resource if you already know what you're looking for. But without the proper language to describe the thing you want to solve a problem, like a helicoil. Helicoils can be incredibly useful for lining, say, a plastic component with metal threads so that you can get a fastener in and out of it without risking damaging the plastic and the threads marring over time. That's great. Trying to describe a helicoil in Google when you're not 100% sure it's what you need, thing that does threads in plastic, doesn't yield you much. And it's a universe of difference between that and an expert who has used them before. And so I've been doing my best to find people who are domain experts who have a lot of expertise in, say, like Carrie has fitting things to the body, or like Jim has casting materials and understanding the chemistry of material casting, the chemistry of binding and adhesion. It's incredibly valuable to have them as an input so I can keep myself from reinventing the wheel, so I can keep myself from going down blind alleys and ending up at dead ends. And it's something that I'm very excited about working in the domain that I do. I have a lot of ability to look at the open source work that has been published, the people's videos on how they do fabrication, and pick and choose from successful designs and how to lead what I'm doing. I can look at what hasn't worked before, say in terms of 3D printed fasteners, like methods for getting molds together, and build off of good work. Uh, Getting the NASA grant is currently my most exciting thing in soft robotics. So having done work on the proposal, putting together the initial prototypes, creating a new system of molding just for that, and then having that come off, having people have the faith in me to trust that I can keep delivering the quality of work that they need for an innovative project like this. I'm very flattered and I'm very excited. I consider it a huge success, especially that I now, through performing my duties on the SBIR, I'm giving presentations to NASA every month or two. I'm getting to talk with people from JPL. I'm getting to talk with people who have been designing and building spacesuits for 30 years. And so, aside from it being incredible validation that I'm doing work of good quality that other people respect, more than that, the opportunity to talk with people who are so well renowned in their field and really know what they're talking about when it comes to space flight, it's incredibly rewarding. Well, ideally, I can build Super-Releaser as a company to the point at which we can fund a research track and a development track. So right now, I spend as much time as I can on client project development, where I'm making robots and paying the bills. And it's very exciting, but there are so many ideas to pursue that also involve the technologies that I've built that underlie all of these robots that I'm building for specific people. I would love to be able to make them more sophisticated. I'd love to be able to go down different tracks to understand, when an interesting thing happens, when, say, two things adhere, or that material completely drips through another material, that it completely interpenetrates some foam. Oftentimes that speaks to an interesting potential exploration and possibly something very useful on the other end. But staying focused and on track and delivering is incredibly important. I would love to, at some point, be working with large enough clients to have a confident roster of clients and devices that I can spend more time and have full-time researchers exploring those, that's odd moments in soft robotics and making innovations on top of the work that we've already produced. So I feel reasonably close. It's great working with the contractors that come through. It's great having clients like NASA, but I don't think it'll be very long before I'm working in a larger group of people. The thing for me is as the core of the company is I need to always be wearing all of the hats. I need to be as diligent in managing expectations and responding to clients and their needs as I do in the research that I'm doing. So it's an interesting fight, but it feels very worth fighting. So thank you so much for giving me the opportunity to answer some questions. I'm excited to see what you can do, and please be in touch. Thank you so much.